class. This is another video from 6.2. We're going to be talking about something that we're going to call the definite integral. So far we've learned about Riemann sums as a way to approximate area underneath a curve. And we hopefully have noticed that the more subdivisions we have, the better our approximation, right? The more rectangles we have. Well, what if we had infinitely many subdivisions? So this is a concept we used in first semester, right? When I want to approach as many as I can, right? I'm approaching infinity. This is a limit. So I am taking the limit of a sum of all these rectangles, right? So here was the height of the rectangles, here was the width of the rectangles, and my number of rectangles or subdivisions there. Well, I want the limit of this as n goes to infinity, if we have infinitely many rectangles. So we actually have a different way of notating this. And we're going to see this a ton second semester, so we're going to get really comfortable with this. But this is called, when I take the limit as n approaches infinity, we're going to get the actual area under the curve. So we call that the integral, okay? And it's kind of this long, elongated S, okay? This is the integral symbol. And we put these same values here and here as our upper and lower limits of integration. And then our function goes here, and you guys might remember this from first semester as well, but delta x, we're going to call that dx, okay? And so I'm going to kind of just label these different parts. So this value here is our lower limit of integration. Okay? Whatever function we are taking the integral of, that is called the integrand. Dx could be different. It could be dt, du, ds, whatever it is. So whatever variable there, that is our variable of integration. And then our upper limit is here. Okay, so those are kind of the different parts of an integral, okay? And so basically this first example is just, can I change this limit and write it in this notation, okay? So we're going to do some more kind of strategies of how to find integrals without using Riemann sums. Today we're still going to be using some Riemann sums, and we're just going to kind of get comfortable with the notation. Okay, so here, again, we are going to write this as a integral. Okay, and they want me just to do from 2 to 6. So these are my intervals of integration. This is my lower and upper limit. So here's my integral symbol, kind of the elongated S. 2 is the lower, 6 is the upper. My function here, I don't need the x sub I because we're not dealing with I anymore when I write it as an integral. So I'm just going to write it as x squared plus 3 is our function, or our integrand. And instead of delta x, dx. So this would be the same exact thing as this, just a different way to notate it and to write it. Okay, so you'll notice here, this is, again, we're still going to use Riemann sums in this section. We're going to move forward away from Riemann sums in our next section. But right now, we're still going to use Riemann sums, but we're just going to get comfortable with this notation. So this says, use a right Riemann sum with two subdivisions to find g of x dx, the integral of gx dx, where g of x is this function. Okay, so here from 3 to 1, right, this is how I can find delta x. We need that for the Riemann sum. 3 minus 1, and we're cutting it into two subdivisions. So I get delta x is 1. Okay, so my notation here, you guys. Sorry, we're not a let. Apparently I need to. There we go. Okay, so my integral, this is not the exact area yet. We're still using a Riemann sum to approximate. So we can say the integral of, from 1 to 3 of gx dx is approximately, right, because we are using a Riemann sum to approximate this area. So Riemann sums, right, we take the delta x, which is 1, and we multiply by the heights. And they want the right heights, so again, here's my intervals from 1 to 2, and then 2 to 3. So my right heights are going to be f of 2 and f of 3. So we've got 1 times f of 2 plus f of 3. All right. Oh, sorry, I put f. This should be g because we are using g of x, not f of x on this one. So g of 2, g of 3. Okay, so now I find g of 2, right, by just plugging into this function. So we have 1 isn't going to change anything but g of 2, so 2 plus 2 is 4, squared is 16. 3 plus 2 is 5, squared is 25. Add those together and we get an approximate area of 41. So the value of this integral is approximately 41. Again, we still use Riemann sum right now to get an approximation. Okay, number 3, same thing. We're seeing the integral notation. Sorry, this dx should not be under the square root. It should be outside. Okay, so we're approximating this integral using, this time we're going to use a midpoint Riemann sum, and then we're going to use a calculator to evaluate. And I'm going to show you how to do that here. Okay, so approximate using a midpoint. All right, so, oh, and sorry, they're missing one piece of information. We are going to use 5 subintervals of width 1. Okay, sorry, we need that piece too. All right, so here we have the integral from 0 to 5 of 25 minus x squared dx is going to be approximately, using our midpoint sum. Okay, if I think about my intervals, right? So we got 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 4 to 5, right? My delta x, 5 minus 0 over 5, because we're doing 5 equal subdivisions, which is 1, which should match what they asked there. Okay, so we have 1 times, okay, so we're using the midpoint, right? So the midpoint between 0 and 1 is 0.5, so that height is going to be f of 0.5, okay? And then halfway between there, f of 1.5, f of 2.5, f of 3.5, and f of 4.5. So using those midpoint x values, and then we're finding the y values that go with it to get the heights. Okay, I went ahead and used my calculator. You guys have already calculated these, so plugging in 0.5 here for x, f of that is about 4.974, 4.770, 4.330, 3.571, and 2.179. Adding all those together, we get an approximate area of 19.2824, excuse me. Okay, so now it also says then use a calculator to evaluate. So we can actually use graphing calculators to evaluate integrals, and this will give us the exact area. So this, remember, is an approximation. We're going to see what the exact area is. So on your calculator, I'm going to write the steps here. Okay, so we're going to hit math, then option 9, which says function integrate, like this. Okay, so that's what we're going to select. And then we're going to enter this function exactly as we see it. So we've got from 0 to 5. I'm going to show you guys this on my calculator in 1 second. Okay, and then we're going to get our exact area. All right, so on your calculator, again, we're going to hit math. I'm going to scroll down to option 9. Right there, FN integrate. Okay? And actually, sorry guys, I'm going to show you this on a newer one. Alright, sorry, this one has a little nicer notation. Okay, math. Alright, so this one looks exactly like what's on my paper. So I've got from 0 to 5. My function is the square root of 25 minus x squared, right? And then the variable of integration I want is x. Okay, so I can literally type it exactly as it looks on my paper. This is the exact area from 0 to 5 under this curve. So it is 19.63, I guess it's still rounded, but from a calculator, we can kind of now see how close our approximation was. pretty close actually, only off by 2/100ths about, okay? Or 2/10, excuse me. All right, so that's how you use a calculator to evaluate a definite integral. So there will be times, you guys, obviously, where we have no calculator questions. This is a great way to check your answer using a graphing calculator. Okay, next example. Use a trapezoidal sum to approximate A being this area, shaded area, using 3 equal subintegrals. Okay. Oh, I'm sorry, guys. That is the wrong one. I think that was from our past video. I'm sorry. Wrong page. Okay. This is the end of the 622. Here we go. All right. Okay, so a couple rules about integrals. If the lower and upper limit are the same, whenever I find the integral of that, it's just going to be 0. So if I notice the upper and lower limits of integration are equal, it's going to be equal to 0. In this case, if I have a is greater than b, if I switch the upper and lower limits, then this is equal to the negative of that. So it's the same exact thing, but my upper and lower have switched, so the sign is just going to change. So let's just use those 2 rules here to evaluate these. So I notice right away on A, my upper and limit are the same. That automatically is going to equal 0. Okay? This one, I'm given that the integral of f of x dx equals negative 19/3. Now they want us to find the integral from 2 to 3 of that same function, same integrand. So notice it's almost identical, but my upper and lower limit have switched. So what that means is it's going to equal the same value, but it's going to change the sign. So it's really negative 19/3, which is positive 19/3. So if it's the same function, but I switch my upper and lower limit, my sign changes for what it's going to be equivalent to. Okay, this is just a helpful piece to know about when are things integrable. So if a function is continuous, then I can integrate it, okay, over that same interval. But if it's not continuous, then it may or may not be. So continuity guarantees integration. If it's not continuous, it does not guarantee integration over that interval. All right, guys, that is it for the video. Thanks for watching.